Hello and welcome to this FP2 exam paper walkthrough. This was the June 2024 paper. You were allowed a calculator and the formula booklet. The complex number z equals x plus iy satisfies this equation here. Determine an equation for the locus of z, giving your answer in this form, where a, b, and c are integers. Okay, with a question like this, we're going to substitute in x plus iy for z, collect the real and imaginary parts, and then square both sides to get rid of the modulus. X minus 3 is a real part over here, y minus 4 is the imaginary part. Over here, x plus 1, the real part, and y plus 1, the imaginary part. Then we square them both, and that gives us the real part squared plus the imaginary part squared, but without I. Same over here. Then we can expand everything and collect. Eight y plus 16, x squared, y squared. And bringing them all together, we can see that the x squareds cancel, the y squareds cancel. That's good because this is supposed to be a line. And collecting them together, we've got 8 x's and 10 y's, minus 25 and 2 minus 23. So a is 8, b is 10, and c is minus 23, all integers. Makes me feel confident. Part B, shade on an argand diagram the region defined by this thing as less than or equal to this thing. Don't need to determine the coordinates of the intercepts, that's good. Oh, it's just 1 mark. Okay, we need to remember what this represents, and it represents the line equidistant from the 2 points given. We've got 3 plus 4i, 3, 4. This is the imaginary and this is the real, so that point is about here. And then in the other bracket we've got 1 plus I, so that's minus 1, minus 1, so that's about here. And then the locus goes perpendicular to the line segment connecting those two. Something like that. But we want to be closer or equal to the 3 plus 4i. So this side is the side that we're shading. And that is it. We don't need to worry about the intercepts, so it's finished. On to question number 2. We've been given a statement, and we need to show that the third derivative level is this. So we just go ahead and start differentiating stuff. We want to do the first derivative is already there, so using the product rule, differentiate x gives us a 1, leave this bit, and then leave the x and differentiate this, gives us the second derivative. And we're differentiating with respect to x, so when we do this, we need to multiply by dy by dx. And over here, that's gone. Now we go again because we need a third level of differentiation in here. So this is just the second derivative. And product rule again here. So differentiate x, leave the second derivative alone. Then leave the x alone, and there's our third level derivative coming in. And then here, product rule again. So if I differentiate the 3y squared, I get minus 6y, but I need to multiply by dy by dx. And there is already a dy by dx. Then I leave the 3y squared alone, and I differentiate the dy by dx to get the second derivative there, still 0 on this side. Now I can tidy this up a little bit. There are 2 of these now. And we still have x times the third derivative. I'm going to write this as dy by dx all squared, 3y squared, and the second derivative again coming in here. Now how do they want it to look? We want x and the third derivative by itself and everything else on the right hand side. We can do that. Third derivative here, and we're going to have 6y times dy by dx all squared plus 3y squared minus 2 lots of the second derivative if I factorize that as well as bring it over. Is that? Yes. So a is 6, b is 3, and c is minus 2. And there we go for part A. Given that y equals 1 at x equals 2, determine the Taylor series expansion for y in ascending powers of x minus 2 up to and including the third power. Okay, so we've got x equals 2, and at that point y equals 1. I'm also going to go ahead and get the other information that I need. If x is 2 and y is 1, at the top of the screen there you can see the derivative. So 2 times dy by dx minus 1 cubed equals 4 gives me a 5 over 2 for the first derivative. Now the second derivative is at the top of the screen. So let me do that as well while I can see it. Dy by dx we just said is 5 over 2 plus 2 lots of the second derivative, which is what we're trying to find, minus 3 times y squared times the first derivative again. And if we rearrange all of that, we find that the second derivative is also 5 over 2. Now the third derivative at the top of the screen, putting in x, the thing that we want, 6 times y times the first derivative squared plus 3 times y squared minus 2 times the second derivative. And that one gives a very different answer. That is 40. So dividing through by 2, we get the third derivative is 20. Now I can put all of these numbers into the Taylor expansion, where f of x equals y equals the function at a plus x minus a, the derivative at a plus x minus a squared, second derivative at a over 2 factorial, x minus a cubed over 3 factorial, third derivative at a. All of this information we've already got. The function when x equals 2, this is all happening where a is equal to 2. At the top of the screen there we were told is 1 in the question. Then x minus 2 times the first derivative was 5 over 2 plus x minus 2 squared over 2 times 5 over 2 again plus x minus 2 cubed over 6 times 20. Tidying that up a little bit, not that there's much we can do here. 5 over 4, x minus 2 squared, plus 10 over 3, x minus 2 cubed, and there we go. That is part B finished. On to question 3. Express this fraction in partial fractions. We can do that. N plus 3, n plus 5, make it equal to a over n plus 3 plus b over n plus 5. Multiply everything by those two brackets. We get 1 is equal to a lots of n plus 5 plus b lots of n plus 3. Then let n equal minus 5. When that happens, a is gone, and b is multiplied by minus 2. So b is minus a half. Then when n is equal to minus 3, the b disappears because that's a 0 bracket, and this is 2a. So a is equal to 1/2. That was quite quick, but we've ended up with not the nicest numbers. We end up with 1 over 2n plus 3 minus 1 over 2n plus 5. And that is part A finished. On to part B, hence, using the method of differences, show that for all positive integer values of n, this thing is true where we need to find p and q, and they are integers. So we're summing from r is equal to 1 to n. As usual, I'll just quickly check that matches. It does, except they put r's instead of n's. So we'll do the same thing. Sum 1 to n, 1 over r plus 3, r plus 5 must be equal to, from our work in part A, 1 over 2n plus 3 minus 1 over 2n plus 5. I've already made a mistake, haven't I? That should be an r. Okay, on doing this, we're just going to go ahead and put in the numbers. So we've got 1 over 2 times 1 plus 3, that's an 8, minus 1 over 2 times 6 is 12. Next one, when r is a 2, that's 1 over 10, minus 1 over 14. Next one is 1 over 12, there we go, they've started cancelling, 1 over 16. So that cancels with that. This one will cancel with the next one. This one will cancel with the next one. And then I'm going to go 3 layers deep on the other side. Finishing with r is equal to n gives me 1 over 2n plus 3 minus 1 over 2n plus 5. Going back a step from that, using n minus 1 would be 2n plus 2 minus 1 over 2n plus 4. Back a step again would be 1 over 2n plus 1, 1 over 2n plus 3, and you can see that this one cancels with this one. But previous to that, this one would have cancelled with the one before it, this one would have cancelled with the one before it. So we're left with those last two, and also these first two, 1 over 8 plus 1 over 10. 1 over 8 plus 1 over 10 minus 1 over 2n plus 4 minus 1 over 2n plus 5. Now we've got a bit of work because they wanted it as a big single fraction. Lowest common multiple between those denominators is 40n plus 4n plus 5, which, if my memory serves, matches the answer given in the question. Then we've got 5 lots of n plus 4 times n plus 5 from the first fraction, plus 4 lots of the same thing in the second fraction, so change that to a 9, minus 20 lots of n plus 5 from the third fraction, minus 20 lots of n plus 4 from the fourth fraction. And now we have to simplify all of this. We've got 9n squared plus 9n times 9 is 81n, 5 4 is 20, 180. Minus 20 lots of n minus another 20 lots of n is minus 40n, minus 100 minus 80 minus 180. So they cancel, and I was going to cancel those n's, but they don't quite cancel, do they? Not in their entirety. That gives us 9n squared plus 41n, and I think they wanted it factorized. Yes. Let's pull that n out. And there we go. P is equal to 9, Q is equal to 41. Integers, and finished part B. Part C, use your answer to part B to determine as a simplified fraction the value of this. Okay, if we look at this, we can see, comparing it to this, that r here is 6, and over here, same idea, we can see that r must be 21, because 21 plus 3 is 24, 21 plus 5 is 26. So what we're doing here is the sum from 6 to 21 which is the sum from 1 to 21 minus the sum 1 to 5. I'll rewrite that down here. Sum of 1 to 21 minus the sum of 1 to 5. And we've got what the sum is, given n, on the screen right here. So that's 21 times 9 lots of 21 plus 41, divided by 40 times 21 plus 4 is 25, 26. So I've just put n equals 21 into this expression here. We're going to do the same thing here with n is equal to 5 and subtract. So we've got 5, 9 times 5 plus 41, divided by 40 times 5 plus 4, 9, 5 plus 5 is 10. Stick all of that on my calculator, and my calculator tells me the fraction 194 divided by 2925. And there we go. Part C and the question finished. On to question number 4. Show that the substitution y squared equals 1 over t transforms differential equation number 1 into differential equation number 2. I can see looking at the first equation that we are going to need y as well as y squared, or perhaps instead of y squared. So if I write that like that, we're also going to need dy by dx, and that is dy by dt, which we can find out, times dt by dx using the chain rule, and dy by dt is minus a half t to the minus 3 over 2. So that's an expression for dy by dx, and we've got an expression for y, so we can get y cubed as well. Now I just need to put it all into the equation at the top of the screen there. Dy by dx plus y is equal to xy cubed becomes, my expression for dy by dx, minus a half t to the minus 3 over 2 times dt by dx plus y, t to the minus a half, equals x. That's fine, we leave it like that. And y cubed is t minus 3 over 2. Now we can see that the equation given in the question at the top of the screen there, dt by dx needs to be by itself. So I'm going to multiply this by minus 2 t to the 3 over 2. And that will get rid of this bit and leave me with dt by dx by itself. Consequence of that is I get minus 2 lots of t here, which actually looks nicer, and equals minus 2x here, which matches the equation. So that's finished. Part B, solve the second differential equation and determine y squared in terms of x. So we're solving this now. This is in the form dy by dx plus py, where p is equal to minus 2. So our integrating factor, which is e to the integral p dx, is equal to e to the minus 2 integrated e to the minus 2x. So the reason we find that is to multiply all of this equation by that. And the reason we do that is so when we integrate this, the left-hand side is an exact differential, and it is e to the minus 2x times t. And you can see if you differentiate that, you do indeed get the expression immediately above it. Now, on the right-hand side, we're going to have to integrate this, which is looking like integration by parts. To do integration of parts here, I'm going to make my u term the minus 2x, so when we differentiate that, we have no x's left. That means the v prime needs to be e to the minus 2x. When we integrate that, we get minus a half e to the minus 2x. Integration by parts, we're doing uv prime gives us uv minus integral vu prime. Applying that gives me u times v, so that cancels quite nicely. X e to the minus 2x minus the integral of v times u prime. Those minuses cancel out, the 2's cancel out, so we get e to the minus 2x dx, which is quite easy to integrate. So we've got x e to the minus 2x. The minuses cancel as that comes down, and that is plus half e to the minus 2x. Add in the constant at this point, and the left-hand side is unchanged like this. Now I want t equals, not e to the minus 2x equals, so multiply everything there by e to the 2x. And that's why it's important to have your constant already there, otherwise it looks like this disappears and is no longer in the equation, but it is, because it comes in here. Now I didn't want t either, I wanted y squared, and oh, it's a 1 over t. I was going to say we just change that into y squared, but we don't. So 1 divided by this is equal to y squared. So I'll be a little bit lazy here and just put brackets around it and raise it all to the power minus 1. And that is finished. Was there a part C? No. Okay, question done. On to question number 5. Use algebra to determine the values of x for which this is true. This is a fairly standard approach to this question, but it looks like there's a lot involved. We've got a 1 there and we've got 2 brackets. So I'm going to be multiplying both sides of this inequality by the square of both of those brackets. So we get x plus 1, and one of those will end up on the top for each. But on the other side, we've got x minus 3 squared and x plus 2 squared times by this 1 here, minus 2 lots of x minus 3. One of those will cancel with this, but none of these will cancel. That's quite a lot of brackets in there. I'm going to move the 2 right-hand terms onto the left. A bit annoying to have to rewrite it all, but I want to be clear what I've done for the examiner. X minus 3 squared, x plus 2 squared, plus 2 x minus 3, x plus 2 squared. Now the fact that there are lots of brackets works in my favor, because lots of them will factorize out. We get x minus 3 and x plus 2. I say a lot. 2 of them factorize out. X plus 1 here. And then there's both brackets left here. So let me just expand those. We get x squared minus x minus 6 for the 2 brackets left in that term. And there's a 2 and an x plus 2 here. So if I expand that, we get 2x plus 4. So I didn't need all those curly brackets in there, but just letting you see the 3 separate terms from the line above. Now I can collect all of this, and we get a minus x squared plus 4x plus 11. That doesn't look like it's going to factorize. No, I'm pretty sure it won't. So let's have minus 4 plus or minus the square root of 16 minus 4 times a times c, all over 2 times minus 1. And that gives me 2 plus or minus the root of 15. And over here, x equals minus 2, and x equals 3, and these are all the critical values. Just remember that x can't actually equal 3 and minus 2 in the original inequality because they're in the denominator, so I can't include the equals part of the inequality when I write those at the end. But for now, just thinking about how this looks, this negative here tells me it's a negative quartic. So if I expanded all this out, I would get minus x to the power 4, and that's enough to tell me the shape of the graph. I've got 2 positive critical values and 2 negative ones, so it looks something more or less like this. 2 minus root 15 is not quite as big as minus 2, so this one here is minus 2. This is 2 minus root 15. This one is 3, and this one is 2 plus root 15. And we want when this is less than or equal to 0. This part of the graph is less than equal to 0. This part of the graph is less than or equal to 0. And so is this part. We've got 3 different bits. So when x is less than but not equal to -2, because like I said with the original here, x can't equal -2. And then between 2 minus root 15 and 3, where it can equal the one on the left, but it can't equal 3 for the same reason. And then x greater than or equal to 2 plus root 15. So here are the final solutions for that question. That wasn't too bad for 6 marks. On we go. Question number 6, transformation. So we've got our usual approach, jumping straight in without even having really read the question. That's a bad thing to do. Let's not do that. The transformation t from the z-plane to the w-plane is given by this. Given that t maps the imaginary axis in the z-plane to the circle C in the w-plane, determine the coordinates of the center of C and the radius of C. Okay, there is an important bit of information in here. The imaginary axis is what we would normally think of as the y-axis. So that happens in our usual xy situation when x equals 0. And it's the same idea here because z is x plus I y. We're saying when the real part is equal to 0, so x equals 0 means this real part of your z expression equals 0. That's going to be useful information later. For that to be useful, we are going to need to do what I started doing here. We want to find z in terms of w, and then we'll substitute in w equals u plus vi, so that we can separate the real and imaginary parts, and then we'll go ahead and set that real part equal to 0. And hopefully that will give us a circle equation. So back over here, we've got wz plus w equals z minus I. Try and avoid too many negatives, so we'll move the I over here and have the minus wz here. So that's 1 minus w. So z is equal to w plus I over 1 minus w. Now we can substitute in u plus vi for w. Otherwise we wouldn't be able to split the real and imaginary parts because the w contains both. U plus v plus 1 lots of I. 1 minus u here minus vi. Now we need to be able to get that imaginary part out of the denominator, again, with an aim to splitting this into real and imaginary parts. To do that, we do something similar to rationalizing. We do the plus version of the same expression, top and bottom. And the denominator is about to get easier, because we get this one squared. When they interact, this times this and this times this, they cancel out. So then we get this times this, which is just minus v squared I squared, becomes plus v squared. In the numerator, this times this will be a real one. This times this will also be a real one, and we get I squared becomes a minus. Then the other two will be imaginary, this times this, so we've got plus v plus 1, 1 minus ui, and this one times this one is just plus uvi. And I don't need to do anything else with this actually, because I can already see the real part here. This is going to be the real fraction, and I know that this is the part that will equal 0, so I'll just extract that right now, expanding the brackets in the numerator. Give me this, and the denominator I won't bother because that's going to disappear when I multiply across. So u minus u squared minus v equals 0. Don't like all those negatives, let's bring that on the other side. U squared plus v minus u equals 0 instead. Now we need to complete the square. So u minus a half all squared takes care of this term and this term, but I have to get rid of that quarter that generates. plus v plus a half generates this term and this term, but I have to get rid of the quarter that generates as well. Collect those quarters on the other side, give me a half, u minus a half squared, plus v plus a half squared. So the center is at half minus a half, and the radius is the square root of 1 over 2, which is the same as root 2 over 2. And that is, oh, that was it. That was the whole question. Transformation done, fairly standard. Given that y equals e to the x sine x, show that the sixth derivative is k times the second derivative. Wow, 6 derivatives. Okay, let's get straight on to this. dy by dx, I'm going to leave the sign alone and differentiate the e to the x, which doesn't change. Then of course we're using the product rule here, so now I need to differentiate the sign, which becomes a cosine, and leave the e to the x alone. So there's the first one, fairly quick. Second one is very similar. In fact, the first term is exactly the same. So this bit is going to produce this again. So e to the x sine x plus e to the x cosine x. Now we need to look at this second term here. Something similar is going to happen when we differentiate e to the x and cos x stays the same. And then we differentiate cos x and we get minus sine x, and e to the x stays the same. So that's not going to make too many terms as we go because of that cancelling there. That's not too bad either. Continuing on. Now we've got 2 of these, but we've already differentiated that. You can still see underlined here to give these 2 terms. So the 2 isn't going to make any difference there, except of course that we get a 2 coming on each term. Now the fourth one, we have done both of these more or less already in the process so far, so we can just recycle what we already know. E to the x sine x produces these 2 terms, and e to the x cos x produces these 2 terms. We just need to be careful with the constants and the negative signs. So the first one produces what we've got just above. And then the sine x produces a negative version of 2e to the x sine x, 2e to the x cosine x. And now these 2 cancel, and the other 2 combine together to give minus 4e to the x sine x. And the fifth derivative, minus 4e to the x sine x minus 4e to the x cosine x. Basically the same thing as this, but with a 4 instead of a 2. Now the sixth derivative, minus 4 lots of e to the x sine x minus 4 lots of e to the x cosine x. I was looking back up here for that bit. Now the next one I'm going to be looking again here, but with a minus 4 in front. And this term already is a negative in the previous one, so that becomes a plus in this one. And then these 2 cancel out, and that combines to give minus 8e to the x cosine of x. Now, what did they want us to prove? That should be a constant times the second derivative. Second derivative is here, so if I write that as minus 4 times 2e to the x cos x, then I can replace that with minus 4 times the second derivative. And this, of course, is still the sixth derivative. And that is our final answer, where k is equal to minus 4. Quite a long process, but not very difficult after getting those first ones differentiated. Hence determine the first 5 non-zero terms in the Maclaurin series expansion for y, giving each coefficient in simplest form. Okay, the Maclaurin series expansion is the Taylor one with a equals 0. So that's f of 0 plus x f prime 0 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial. If I can switch to Roman numerals, I hope that doesn't confuse anyone. And power 6. Now it said the first 5 non-zero, but because we've done the 6th derivative in part A, I'm kind of assuming that 2 of these are zeros, so that we end up using all 6 derivatives to get 5 non-zero terms. And the first one, well, the first one is 0, because sine of 0 is 0. So that becomes a 0. First derivative is a 1. Second derivative is a 2. Third derivative is a 2 as well. Fourth, everything with a sign is 0, so the fourth derivative is 0, so there's another 0 term. The fifth one at the top of the screen there is minus 4. And the sixth one is minus 8. Which gives us x plus x squared plus 1/3 x cubed, no power 4s, 1/30th x power 5, and 1/90th x power 6. 5 non-zero terms. I think that was the question finished. Yep. Okay, on to question number 8. Given that t equals log of x, okay, I'm going to write that down, but I'm also immediately going to write down that e to the t is equal to x as well. Show that the second derivative is equal to that fairly horrible looking thing involving y's and t's. Okay, well, we don't have any y's yet, so we're going to have to use the chain rule to write dy by dt, dt by dx. So we need dy by dt's, that's okay, and we've got dy by dx's on the left hand side, and dt by dx is something that we can find from this one here. Dt by dx is equal to 1 over x. So we can put that in, 1 over x, dy by dt, that one there obviously, and that is the first derivative. But we need the second derivative, so we're going to differentiate everything with respect to x, and that is the product rule here. So if you differentiate 1 over x, you get minus 1 over x squared, and leave this one alone. Then we need to differentiate the other one, and leave 1 over x alone. But when you differentiate dy by dt with respect to x, you need to differentiate with respect to t and times by dt by dx. You're applying the chain rule as part of your differentiation here. So this becomes the second derivative with respect to t, but because we're actually differentiating with respect to x, we need to multiply by dt by dx. But that's okay, because we already know what that is. We've already used it once. So this one's fine, no problems here. And then this one becomes 1 over x squared. second derivative with respect to t. I've missed a minus. There's the minus there. And now we need, in terms of t, we don't want any x's at all. But we also know here that x is equal to e to the t. So I can substitute that in now. I get the second derivative of y with respect to x is equal to minus e to the minus 2t. If I put e to the t in there, and in here we get plus e to the minus 2t. And then it wanted us to factorize that. And put my positive in front. Like that. And that's the second derivative of y with respect to x. Let me just double check. Yes. Hence, show that the transformation t equals log x transforms the differential equation number 1 into the differential equation number 2. Okay, that's fairly awkward. I'm going to copy and paste that down, and we're looking to transform it into a fairly normal second order differential equation where the two derivatives have a constant 1 and minus 1. Try and hold all of that in my head. So we've got this information from the question, the derivative that we found just above it. We also know that x is equal to e to the t, so we're going to substitute these two things into the equation given. That gives us e to the 2t from this x squared here, and then this whole expression up here is going to multiply by that, so that's e to the minus 2t, that's nice, they cancel, and then the bracket is left, dy by dt minus 2y. That y is okay, we need y's in the equation, I don't need to do anything with that. For log of x, which is e to the t, so that log and e will cancel, minus 2 lots of log e to the t all squared. So there's nothing going on over here, this is all okay now. We've got the 1 and the minus 1 that we needed. Over here we've got 1 plus 4t minus 2t squared. And hopefully that matches 4t minus 2t squared, yes. Now solve the differential equation number 2 to determine y in terms of t, and then at the end we're going to change that back in part D to get y in terms of x. So for part C we're just solving this differential equation in the usual way. The auxiliary equation in this case is m squared minus m minus 2. That will factorize. Minus 2 there and a plus 1 there. So m equals 2, m equals minus 1, which means our complementary function is a e to the 2t plus b e to the minus t. Now for the particular integral, we want to try something similar to this, so a general quadratic expression. Y is equal to lambda t squared, I almost wrote x, mu t plus nu. So the first derivative, 2 lambda t plus mu, and the second derivative, 2 lambda. Put those into the equation at the top of the screen there. We need one of these, 2 lambda minus one lot of these. I'll just put that straight away. Minus mu. And then we want minus 2 lots of y. And all of that has to equal 1 plus 4t minus 2t squared. So this one here, minus 2 lambda, has to equal minus 2, so lambda is equal to 1. That's a nice easy start. Then this one and this one together have to equal a 4. So we've got minus 2 lambda minus 2 mu equals 4. And we know lambda is a 1. That gives mu is equal to minus 3. Then the remaining terms, 2 lambda minus mu minus 2 nu has to equal 1. That's a 2 minus minus 3 minus 2 nu minus 4. So nu is equal to 2. So our particular integral is t squared minus 3t minus 2, plus 2, and our general solution, which is the complementary function plus the particular integral, is equal to a e to the 2t plus b e to the minus t plus t squared minus 3t plus 2. We don't have boundary conditions, so that is the general solution. Hence determine the general solution of the differential equation number 1. So we're just changing our t's back into x's using log x. Part D, t is equal to log x, put that in, y is equal to a e to the 2 log x plus b e to the minus log x plus log of x squared minus 3 log of x plus 2. It didn't give us a particular format, but it would be strange to leave logs in exponentials like that, because this 2 can become a mini squared there, and same with the minus 1 on the next one. So that will become ax squared plus bx to the minus 1. The rest would stay the same. And that is our general solution. Question 8 finished, and usually that's the end of the paper, but here we've got to question 9. Use de Moivre's theorem to show that cos 6 theta is equal to that horrible looking thing. This is going to take some time, but it's a very systematic process. We're using the fact that cos theta plus I sine theta to the power of n, i.e. de Moivre's theorem when the modulus is equal to 1, is the same as cos n theta plus I sine n theta. So if I change that n to a 6, it looks like this. So when we expand this bracket using our usual binomial theorem expansion, we can equate the real parts to the cos 6 theta on the right hand side. We do, however, have to expand this, which is not so quick. So we've got that 6 cos 5 theta I sine theta. If I remember correctly, the next one is 15 cos 4 I squared sine squared theta, and then 20. Your calculator can produce the Pascal triangles if you don't remember them, with the n choose r button. Squared I4 sine 4, 6 cos theta I5 sine 5 theta, and then I6 sine 6 theta. Now we need to simplify this by getting rid of the i's where we can. So this first one we can't. Just a single I is stuck, that's an imaginary term. This one becomes minus 15 cos power 4 sine squared theta, that's a real term. This one becomes a minus, but there is still an I left over, so that's an imaginary term. This one becomes a plus 1 when you get rid of both I squared powers. This one, 4 of those 5 become a plus 1, but then there's still one left, so that's still an imaginary term, and this one becomes minus sine power 6 theta. If you can ignore the annoying blue dots on the screen, we're now going to equate the real terms there with the cos 6 theta on the right hand side of the original equation. Alright, like this, and that's cos 6 theta minus 15 cos to the 4 sine squared, ignoring all the I terms, 15 cos squared theta sine power 4 theta minus sine power 6 theta. Now that's great, but we need it all in terms of cos, not sine. So now we're going to have to use the fact that sine squared theta is equal to 1 minus cos squared theta. But we're also going to need sine power 4. So sine power 4 theta is just the one above squared, so 1 minus 2 cos squared theta plus cos power 4 theta. And then we also need sine power 6 theta, which is the 2 above it multiplied together. So if I put brackets, that one times by this one, if I try and do that directly, try not to mess it up, we've got one lot of each of these. Less likely to mess it up doing it this way, and then minus cos squared times each of these. That's a plus 2 cos power 4 and a minus cos power 6. And I can simplify that a little bit. I've got minus 3 cos squared thetas plus 3 cos power 4 thetas and a cos power 6 on the end. Substituting those in here, here, and here, that gives us cos 6 theta. It's a lot of writing in this one, but it is very systematic. You do the same sort of thing each time you come across a question like this. 1 minus cos squared plus 15 cos squared theta, 1 minus 2 cos squared theta plus cos power 4 theta. And yes, of course, it is very easy to make a mistake. Like that. That's not right. Squared theta. Make sure I can read my own handwriting. Now I'm going to expand those brackets. Minus 15 lots of cos power 4 plus 15 lots of cos power 6 plus 15 cos squared minus 30 cos power 4 plus 15 cos power 6 minus 1 plus 3 cos squared minus 3 cos power 4 plus cos power 6. And when I simplify this, hopefully we get what was given to us in the question. We've got 1, 16, 17, 32 cos power 6 minus 15 minus 45 minus 48 cos power 4s, 15, 16, 17, 18 cos squareds, and a minus 1 stuck on the end. Does that match? 32 minus 48, 18 minus 1. It does, yeah. Okay, no silly mistakes made. Hence, determine the smallest positive root of the equation this. Immediately check, make sure they match, and they do not match. That's annoying. You can see that this is an extra 50%, or 3 over 2 times 18. This is 3 over 2 times, this is 3 over 2 times, and this is not. So I want this to be 3 over 2 times bigger, so I want this to be 3 over 2 here. In order to do that, I need to subtract a half, but the consequence is that needs to happen on the other side as well. Everything else can then stay the same. So I'm going to do that, if I can remember. So 3 over 2 times that would be 48. X to the 6 minus 72x to the 4 plus 27x squared minus 1 equals 0. And we're changing that equation into this equation by subtracting a half on both sides so that I can take a 3 over 2 out of this and make the numbers match. Now that might not be the way that you think of it, and that's fine, there are other ways to think of it. Now I'm going to let x equal cos theta, and at the same time I'll take the 3 over 2 on the other side, so that'll give me 32 cos 6 theta minus 48 cos 4 theta plus 18 cos squared theta minus 1 is equal to minus 2 over 9. No, it doesn't, because I've got a minus third there for some reason. Why on earth have I done that? That would be minus 2 over 6, minus 1 over 3. Talk about a misread. Now, the whole point of doing all of that is so that we can use what we've got at the top of the screen there to change this left-hand side into a cos 6 theta, which is much easier to solve in terms of an equation. That gives me quite a horrible decimal. I think I'm going to need more room because we're going to have lots of answers here. 6 theta is equal to 1.91063 ... And then whether you like a cast diagram or thinking of it just in algebraic sort of terms, or the way I do it, which tends to be going back to the graph, we need more results. So minus a third is about here. That's coming up here. So if I do 2 pi minus that number, I get a second answer, which is 4.37255 ... But because we're going to divide these numbers by 6, I need to keep going. If I add 2 pi to the first one, I get 8.19381 ... Add 2 pi to the second one, I get 10.65573 ... Now if I add 4 pi to the first one, I get 14.47700 ... And 4 pi to the second one gives me 16.93892 ... Now if I divide all of these by 6, we find that they are still within the 0 to 2 pi range. And I've just realized I should have checked what the range was. It doesn't say, but we need the smallest positive root. Okay, now be careful here, because the smallest positive root shown here for 6 theta is obviously also going to be the smallest positive root for theta, but not necessarily the smallest positive root for x, because x is equal to the cosine of theta. So I'm going to go through the process, find all 6. Time consuming, but it guarantees I'm going to get it right. This one is 2.8231. This one over here, doing it in a slightly funny order, just because of which one was on the calculator first. And this one, 2875. This one, 1.36563. This one here, 2.412833. And this one, 1.77595. Therefore, x, which is equal to the cosine of theta, here is 0.9497. Here, you can see is already smaller, 0.74600. Here is 0.20372. Here is a negative, so I don't need to worry about that. This one over here is a negative. You can see a pattern forming here, I'm sure. And as you would expect, this is the negative of that result. Well, it's a lot of work to find the smallest positive value, which is here. So x is equal to 0.204 to 3 decimal places. Was it 3 decimal places? Yes. 0.204. That is the end of question 9, but believe it or not, there is a question 10 in this paper. This was a beast of a paper. Figure 1 shows a sketch of a curve C with polar equation this, and a line with polar equation this, where k is a positive constant. Given that C and L intersect at point P, OP is equal to, it's really awkward, 1 plus root 3 over 2. So that's the radius at that point on both the line and the curve. Determine the exact value of k. To determine k here, I'll want to know both r and theta. At the point P, we already know r, so I can use this equation here to find theta. So we do r, oh, that's a big question as well. 1 plus root 3 over 2 is equal to 1 plus cos theta. So we know cos theta is root 3 over 2. That gives us theta is equal to pi by 6. And then we can put that into the second equation. So it's still r, it's still 1 plus root 3 over 2. But this time is equal to k times secant. So that's divided by cos theta. We just found that cos theta was root 3 over 2. So that's k over root 3 over 2 is equal to 1 plus root 3 over 2. This doesn't look like it's going to be a very nice k value. Exact value, okay. That makes me more confident. That's root 3 plus 3 over 2 is 2k. If I call that 2 root 3 plus 3 all over 2, then k is equal to 2 root 3 plus 3 all over 4. Suitably horrible k value. Part B, the finite region R shown shaded in figure 1, bounded, use integration to find the area, where p, q, and r are simplified rational numbers. So we're going to get fractions here, and we've already got fractions and surds. This is not going to be a pleasant, but 7 marks and it finishes the paper. So let's have a look. What are we doing? Finding the area. In this case, we're going to go from p, which was pi by 6 for theta, up to wherever this finishes, pi. And that will give us this region here, but not the whole thing. We're also going to need this triangle. But we know that this is pi by 6, and we've already found cos of pi by 6. So if we get sine of pi by 6, we can use simple trigonometry to find these two sides here. So I'm actually going to do that first while I think of that. So the area of the triangle is equal to a half base times height, where the base is equal to 1 plus root 3 over 2 cos of pi by 6. And the height then is equal to 1 plus root 3 over 2 times the sine of pi by 6. That one is 3 plus 2 root 3 over 4, which makes sense because that matches our k value, which is what this would be when theta equals 0. So that's this length here. Nice to have the confirmation. And this one is 2 plus root 3 over 4. Putting that into our area formula for a triangle gives me a very horrible 12 plus 7 root 3 over 32. Wow, that was awkward and complicated just to get the triangle. Now we're going from pi by 6 to pi using the curve in our usual half r squared d theta integral. So we're going from pi by 6 to pi of a half r squared d theta, where r is 1 plus cos theta, and that gives us 1 plus 2 cos theta plus cos squared theta. Now cos squared theta, we're going to need a double angle formula. Cos 2 theta equals 2 cos squared theta minus 1. So that will be a half plus a half cos 2 theta to give me cos squared theta. So that will be the integral of 1 plus 2 cos theta plus a half cos 2 theta d theta, with a half in front still. That half and the 1 can add together to make a 3 over 2. And it's pretty awkward already, so I'm going to go ahead and put that half in. Cos theta, quarter cos 2 theta, and that will give me 3 theta over 4 plus sine of theta plus 1/8 sine of 2 theta from pi by 6 to pi. Okay, well at least the sine of pi and the sine of 2 pi is 0. So that gives me 3 pi by 4 plus 0 plus 0. And then pi by 6, 3 pi by 24. Sine of pi by 6 is a half. Sine 2 pi by 6 is root 3 over 2. So that becomes root 3 over 16, which gives us 5 pi over 8 minus a half minus root 3 over 16. And we have to add that together with the area of the triangle at the top of the screen there. So 12 plus 7 root 3 over 32 plus 5 pi over 8 minus a half minus root 3 over 16. Start with the easy one, minus 1 over 8. And for the root 3, that's 5 over 32. And, okay, maybe the pi was the easy one. So we've got pi's, root 3's, and a fraction on the end. pi root 3 fraction on the end. So just finishing it off, writing it exactly how they wanted it. And we did end up with fractions, so that makes me more confident. Q is equal to 5 over 32, R is equal to minus 1 over 8. That was a really big paper, but we have finally got to the end of it. Question 10 finished. I hope that was helpful for you.